Again, my name is Harry Hockheiser, Director of the MIDAS Coordination Center. And I want to introduce today, we're very pleased to have Karen Holcomb join us. Karen is a biologist at the CDC. She has a PhD in epidemiology from UC Davis, where she's done a lot of interesting work on the impacts of climate and mosquito control on the transmission of vector-borne diseases, and has done a lot of great field work. And one thing that I noted on her LinkedIn page that sounded particularly cool is that she's done some work on a program called Girls Outdoor Adventures in Leadership and Science, which sounds like something my older daughter would have loved if she'd been able to take that. So sounds like a great program. She's going to talk to us today about evaluating West Nile virus prediction in the United States. So Karen, apologies for the delay. Please take it away whenever you're ready.
No problems. Thank you so much for the introduction. Let me see if I can. Host has disabled participant screen sharing. Oh, there we go. Perfect. Okay, let's see if we can turn on my video. Nope. Okay. Bandwidth issues, I'll probably just keep my video off. But thank you so much, everyone, for coming to the seminar today. And yes, I also apologize for all the technical difficulties that we've had this morning. But I'm going to give you an overview of what I have been doing through my postdoc position since I finished at UC Davis. And the primary theme of this talk will be on West Nile virus and evaluation and prediction in the United States. And for this work, I was a joint postdoc between NOAA and CDC for this work. There we go. And to give you a little bit of context about this unique postdoc position, this position started due to interest from all of our NOAA colleagues and friends who were very interested in supporting public health in terms of improving prediction or capacity, whatever they could do for those climate-sensitive diseases. And they decided to start with West Nile virus. And this slide gives you an overview of who all are the major faces of everyone I was interacting with on a weekly-ish basis. So this was a very unique postdoc position where I got to act as a bridge between agencies, both, excuse me, I have a poll popping up. Both through NOAA as well as CDC and multiple branches and locations for all of them. So I was able to bring together and cross agencies, providing translation of products and ideas and hopes and dreams. And this postdoc was logistically funded through UCAR, but I was positioned most with NOAA and CDC for this collaboration. And starting in, West Nile virus is the leading cause of mosquito-borne illness in the United States. It's one of the vector-borne diseases that's maintained between birds and Culex mosquitoes. And an infected mosquito can bite either a horse or a human and cause clinical disease. And for this presentation, I'm going to focus on human infections. So once infected, about 80% of people are asymptomatic. About 20% of infections result in a febrile illness with aches, pains, nausea, vomiting, sorts of feeling cruddy for a little bit, but most people recover just fine from this form of the disease. And about less than 1% of all infections results in the neuroinvasive form of the disease. So about 1 in 150 people have the virus, which enters their central nervous system. And about 10% of those who acquire this neuroinvasive form of the disease actually die from the disease. So it is a severe form of disease. And for modeling this disease, we are most often utilizing neuroinvasive cases because these are the most severe and most likely to be complete data set for human cases across the US for reporting. Because if you get the neuroinvasive form of the disease, you are likely going to go to the hospital and get a correct diagnosis. While if you have the febrile form of the disease, there's less likely that you're actually going to go into the hospital or doctor and may not even get tested for West Nile virus. So some of the major mosquito species that are involved in this transmission of this disease are the Culex mosquitoes. And I've put some spatial maps here to provide some context of how the primary mosquito species varies across the US. For Culex pipiens and Culex quinquefasciatus, these mosquitoes generally breed in more urban locations. So in storm drains, sewers, things that hold water within urban locations. And in contrast, Culex tarsalis breeds more in those agricultural areas like rice fields or flooded irrigation sorts of things. So the predominant West Nile virus vector varies spatially across the US, as well as what is the primary land use or breeding habitat that these mosquitoes are utilizing. West Nile virus was first introduced in the United States in 1999, and since then it has spread across the US and become endemic, with the highest average annual incidence in those Great Plains states, so North Dakota, South Dakota, down through Colorado, as well as high numbers of cases reported in California and Chicago areas, as well as some along the East Coast and more New York sorts of locations. So there's a large spatial heterogeneity in where West Nile virus cases occur on average. And then if we look individually at years since West Nile virus has invaded the United States, there's a huge variation in spatial heterogeneity in which counties are actually reporting West Nile virus. So these plots illustrate counties that had reported at least one case of neuroinvasive form of the disease, West Nile virus, each one. And the orange number down at the corner indicates the number of counties each year that were reporting at least one case. So there's huge variation across time. And as you look from 1999 through 2004, you can see counties moving across the United States being infected. So you can see that wave of invasion of West Nile virus as it crossed the county, across the state. By 2005, it had reached all the way over to the West Coast and had become endemic in the United States. And if we look at the actual number of cases that are occurring each year, we also see this heterogeneity in incidence, where we have years of very high incidence followed by generally lower trends. So there's almost a cyclical-ish pattern that could be seen for neuroinvasive form of the disease across time. However, this is not strictly a single pattern of neuroinvasive infection across time. And the pattern varies. And it also varies on the county itself. But for space, I did not show all of those spaghetti plots for it. And when it comes to West Nile virus, most of the protection involves personal protective measures or vector control. There is no human vaccine for West Nile virus. So utilizing insecticide repellent, preventing mosquitoes from accessing the house by utilizing screens, and removing standing water around the house are what individuals can do to protect themselves from West Nile. And there's a large number of vector control districts spread across the United States that are engaged in reducing and managing mosquito populations to prevent transmission of various diseases to humans. However, these vector control strategies are very localized and focal by treating locations where mosquitoes are breeding, so treating the water that hold the juvenile mosquitoes, or spraying insecticidal sprays, using backpack sprayers, truck-mounted sprayers, or in cases of high epidemic emergence, utilizing airplanes as well. So we need, while these vector control strategies are effective, they're very localized and short-term in their effect. So having accurate predictions of where West Nile virus hotspots and cases will occur can vastly help improve control of West Nile virus moving forward. So this leads us into the first section of the talk that I'm going to be presenting on the West Nile virus forecasting challenges, which were challenges put on through CSTE and CDC. So CSTE is the Council for State and Territorial Epidemiologists. And the goal was to predict the total number of West Nile virus neuroinvasive disease cases by county in the continental US, as an early warning sort of a system of where are we likely to see those higher numbers of cases or lower, and also evaluate how well can we predict overall. There have been two challenges, one in 2020 and one in 2022. In 2020, 15 teams participated, and they were providing predictions of probabilities for bin number of cases. So this means we gave them a set of bins of like 0, 1 to 5, 6 to 10, 50 to 100, and each one gave probabilities in there for all of the counties in the United States. And I'll go a little bit more into this in the following slides. And the data that these teams were provided with were the total counts of neuroinvasive disease by county for 2000 to 2019. And then similarly in 2022, the teams were provided with data from 2000 to 2021. However, we changed the prediction format to quantiles for this time to be able to better capture the county by county differences in number of cases and provide a resolution around the most likely counties or most likely number of diseases that counties would be reporting. And in 2022, we had 8 teams that participated. Since the 2022 challenge is still ongoing, I'm going to focus on the evaluation that we've been able to do for the 2020 challenge. So the challenge was initially announced in March of 2020, and teams could sign up to participate. Their first submission time point was at the end of April, where they submitted probabilistic estimates for bin number of cases, and I've listed those out down at the bottom of the slide. And the histogram kind of gives you a visual representation of what these forecasts look like for all of the counties in the United States, including Washington, D.C. And then over the next 3 months, teams could submit additional forecasts if they changed their model structure or incorporated more data, like updated climate variables. They were also able to include the 2019 case data that became available in early May of 2022. And then fast forwarding to November of 2021, the case data was finalized for 2020, and we were able to evaluate forecasts. We chose to use log scoring to evaluate the skill and accuracy of predictions. And some of the major questions that we were interested in answering were, do some models have better predictive performance than others? Are there modeling approaches associated with better predictions? And are there county-specific factors associated with variation in skill? So more contextual factors where it's harder or easier to predict West Nile virus. And as I mentioned, there were 15 teams that had participated, and they had a variety of different numbers of submissions that they included. Note that the abbreviations are based on the affiliation of the team lead for the team itself. Most of these came from academic institutions. However, there were some governmental institutions like Los Alamos National Labs and USDA and a public health agency as well. And as you'll notice, looking at the type of data included across these different models, they're very heterogeneous in which covariates were each team decided to include, whether it was climatic data, information on mosquito populations, which were either abundance and infection detections in mosquitoes, or more of a synthetic mosquito population estimate that was built for the entire US. They also looked at human demographics and infections in birds and horses, and land use is that last category. And most commonly in this land use, it was urban areas, crops, wetlands, natural areas, sorts of things to try to get at breeding habitats for those mosquitoes. And in order to provide some benchmark comparisons to how well the team forecasts were performing, we also developed some comparison models. So we started with some very simplistic models for the naive, saying that everything is equally probable. All of the bins have equal probability weights to them. And then an always absent model, which says there will never be cases. And then we built some more historical data models. The first one was built on a negative binomial distribution. So we took the historical cases for each of the counties and fit its own negative binomial distribution and used this to predict future cases. And we fit two versions of this negative binomial to capture data availability at the initial point. So either 2000 to 2018 for the first submission time point, and then 2000 to 2019 cases for following submissions. We also built an autoregressive model. We did a time series analysis of order one, so an AR1 model, which essentially takes the year previous to predict the next year. And we're also, as we know, West Nile virus is a climatic sensitive disease. We also wanted to build kind of a naive climate model where we took our autoregressive model, our AR1 model, and added in a climatic variable. For this analysis, we utilized the mean winter temperature, which is the mean temperature of December, January, and February for the prediction year. So December 2019 through January and February of 2020. And then we also built an ensemble model. This was a mean ensemble that we built utilizing all the teams in the negative binomial forecasts, because the ensemble has been found in other forecasting challenges to perform well and to generally outperform individual models. So jumping into some of the results, this plot illustrates the log score, so the mean skill of each forecast and comparison model at each of the potential submission time points. And 0 would be a perfect score. So we want to be higher up on the plot. And to be able to see a little bit better differentiations between those top models, I've zoomed in to focus on these. And I want to highlight a couple things as we move through. First, in the top scoring models included some of the models that were based on historical distributions, which I've given the star. So the negative binomial model, our autoregressive 1 model, and the team from MSSM, which used an empirically weighted model. We also want to note the performance of the ensemble model. This was in the top third of predictions, and it generally outperformed most of the models. However, it was not the top model in performance, as has been seen in other forecasting structures. And notably, it did not outperform historical data models, so the negative binomial and our AR1. And then if we compare our AR1 model to how well our AR1 climate model was, the AR1 climate model had a lower skill than our AR1 model. So I want to go and investigate this a little bit more with you. The way that we developed our AR1 climate model is we took our AR1 model and then investigated a variety of different climatic variables that we could add into this. So we looked at either mean temperature, minimum temperature, total precipitation on a seasonal, so 3-month grouping of data for winter, spring, summer, or fall. And to account for variation in the amount of information that we would have for predicting for the year, we only used previous information from the whole previous year and only winter and spring for the current year. So for predicting 2020, we didn't use summer or fall data, which would not be available early in the year. And then we utilized our AR1 climate model to iteratively predict years from 2011 through 2020 to be able to capture any variation in effect of the climatic variables across time, and scored them also utilizing log score and selected the best model based on the mean log score. So if we look at how are each of the models performing over time, in the upper left, you'll see the mean log score of all of the 18 models or 19 models that we looked at to compare what their mean log score is. You'll notice that they're similar patterns and overall score together. And then if we go through and rank them, what was the best, and then second, third, fourth down, which is the bottom right spaghetti plot, you'll notice that the AR1 model is always the top model across years, while the AR1 model with whatever climatic variable varies greatly year to year. So if we condense all of that information together to look at the mean across all years, we see that our AR1 T-mean winter, so the climate model that we utilized was mean temperature for winter as our climate variable, which I noted earlier. And just looking overall, we found that the addition of seasonal weather variables reduced skill in contrast to from our AR1 model overall, which highlights that there might be more regional differences in the impact of weather, such that no single one weather variable would be able to predict the whole US at this time. However, this rather simplistic climate driver model still outperformed a large number of the teams. If you think back to the original spaghetti plot I was showing, it was in the top third of models. So it still performed fairly well for being a rather simplistic model. So now let's turn and actually look at spatial variation in how well the models were performing. I'm going to look at our ensemble model, for the last submission time point across all models, to try to understand where are models performing well and where are they not performing well. So a log score of 0 is perfect. So the darker the color is, the worse scoring it is. And just looking at it, we can see that there's some relationship of scoring worse generally in areas that have higher population, like Southern California, areas in Texas, like Houston, Dallas area, as well as Chicago, sorts of things. However, this is not a clear matchup to it, and there's hints of sometimes worse scoring in places that had those higher incidences in them. So another way to look at and kind of tease apart how well were areas performing or not, could look at spatial variation and our uncertainty from that model. So we used entropy to capture the spread of the predictions across all of the bins, and areas with darker fill are those that have more uncertainty in them. And there, notice that the spatial uncertainty that we see here is similar to the pattern that we saw for the log score, where those were performing better or worse. However, it's not exactly the same. So it gives us an idea that maybe uncertainty and log score and the history of cases are impacting where or what, but it doesn't fully elucidate what was the maybe relationship with worse or better log score. So what we did is we did some investigations using regression analyses to look at both climactic factors and then model characteristics, what I'll get into. So for climactic factors, this is looking at just the counties themselves. Where were they scoring better or worse? And for those counties, what were factors that were related to or maybe associated with skill? Was it more climactic variables or land use, the history of the West Nile virus, human demographics in those locations? And then on the model characteristic sides, we're looking more just at which models were performing better or worse based on covariates that were included, and did teams update their models, likely indicating that they updated covariates over time. And due to the heterogeneity between different modeling classes utilized, we weren't able to look at what modeling classes might be associated with better skill or worse skill. So if we look at what were maybe some of those contextual factors with variation in skill, we had 3 variables that came out as highly related. First, total population, historical variation in West Nile virus counts, which we use entropy again, and then minimum extreme winter temperature to try to capture the climactic variables and season distilled down. So anything above our 0 line in these plots indicates that these were characteristics of locations that had better score, and below the line were places that had decreased score. So we're having worse prediction in places with higher populations and higher entropy, so larger variations year to year in the total number of cases. We also see some relationship with the minimum extreme winter temperature. It was kind of in the middle, scoring better in those locations than if you had a colder or a warmer summer. And if we look at the model characteristics that were associated with variation in score, and see that teams that included climate demographics or updated the covariates had increased score on average, and those that included land use or mosquitoes generally had decreased score. And we were thinking that the inclusion, while mosquitoes are very involved in the transmission cycle, we're thinking this reduction in score is reflecting the current heterogeneous nature of mosquito surveillance data across the United States, where there's some districts that do very extensive and routine surveillance of mosquitoes, while other locations have no information on mosquito trapping overall. And then also teasing apart and looking more at probabilities, how well were teams actually predicting events that actually occurred. So what I'm looking at here is calibration, and perfect calibration would be that diagonal dashed line, where if you predicted an event had a 20% chance of probability of occurring, did you actually observe it occurring 20% of the time, sort of a thing. And we see that generally there's underprediction of high probability events, which were the occurrence of low or no cases. I've circled some of these in the bluish greenish circles, where the models overall are predicting, like, let's say 60% probability of an event that's actually occurring more like 80% of the time. So being above the line there, we're under predicting those higher probability events. And on the other side of the coin, therefore, there's under prediction of those low probability events, which were having cases overall. So if we move into wrapping up, what were the conclusions that we're able to learn about West Nile virus prediction utilizing the 2020 challenge? We saw that simple models based on historical incidents performed well. And also notably, the ensemble model did not outperform these historical data models, the negative binomial or our autoregressive model. And the addition of land use or mosquito variables did not improve skill in this instance, potentially reflecting the quality of the data that is available for mosquitoes, and land use is not informing probabilities beyond what we already have included with other covariates. And our analysis of those contextual factors related to variation in skill highlights further areas where we need to investigate, like larger populations, higher heterogeneity in West Nile virus cases, to be able to see, understand how can we better improve predictions in locations that have those characteristics, because these are places that we would really want to have good estimates. And in general, overall, all models were under predicting that there will be no cases. And we're highlighting that there's further investigation of the impact of climate conditions on West Nile virus prediction is warranted. Based on, we were seeing that models that included climate generally performed better than others that did not. However, when we were building our autoregressive climate model, the inclusion of any climate covariate was reducing our skill. So it bears further work to identify those variation in spatial effect and dominant drivers of climate in different locations across the United States to improve prediction. So this last section is going to be a very brief overview of what I am doing to try to understand what are the important climactic factors for large-scale early warning prediction of West Nile virus. And I'm utilizing random forests for this. And as a little background to make sure we're all in the same place, random forests are ensembles of decision trees. And I'm using these decision trees in the regression sense versus the categorization. So we take some training data and fit it and split the data on various different variables that give us the best prediction and outcome. We do this multiple times with different subsets of the training data to build a whole forest of random forests. And then we use the testing data, which was not included in training, to predict overall some outcome. In this case, it would be number of neuroinvasive disease cases. And from my forest, you take all of the different predictions and average them to get one single prediction for it. And then I'm using random forests here in a time series sort of approach, where we need to update a little bit how we're including data into the model such that random forests understand the temporal nature of some of those covariates. So if we want to forecast the time series of cases that we have here, so let's see, we want to predict year 4 utilizing the previous 3 years. So we lag variables 1, 2, and 3. And then when we move to predict the next year, lag 1 now associates with the next year ahead from what it had previously, and thus forward, updating as we go along to include those lagged impacts, and they're temporally ordered in time. So what I'm doing is predicting using iterative direct forecasting for West Nile virus prediction, using multiple years of prediction, incorporate more data overall to get a fuller picture of prediction and what are the drivers of West Nile virus across time. And to capture some of the variation that we are seeing in prediction in our results, we utilized 2-year training windows when fitting each of these models to predict overall. So this increased the confidence interval widths around our estimates. To begin with, they were too narrow and we're not fully capturing all the uncertainty in the training data that we were seeing. And for these random forest analyses, I'm running them in climate region-based analyses. So NOAA has developed 9 different climate regions, which are similar based on large-scale temperature and precipitation regimes. So this also captures some of the differences in mosquito distributions across the US. So I'm fitting an individual random forest analyses to each of the climate regions. So they are separate from each other. And to move beyond the county scale, which varies greatly across the United States and have a standard spatial unit, I fit a hexagonal grid across the United States. So this is what essentially the locations utilized in the model look like in the different climatic regions. And when it comes to the predictors that I'm considering, first are the history of neuroinvasive disease cases. I lag these from 1 through 5 years, try to capture variation in impact and potential any cyclical effects that we are seeing across time, as well as climatic variables. I considered both mean temperature, minimum temperature, and precipitation, both the raw count, so 68 Fahrenheit or 22 centimeters of rain, as well as the anomaly that this relates to based on the 20-year average. So it might be more of deviations from normal that are more driving case counts than the actual climate that it has always been. And I looked at these 0 to 5 years, so including the current year, as well as lags up to 5 years to capture any holdover and change in variation across time, as well as land use of urban crops and wetlands, and demographics from the US Census of total population, older populations, as well as population density. And this is a good point to note that the neuroinvasive cases and the demographics, how I aggregated them up to hexagons, is I took the centroid for each of the counties and assigned it to the overlapping hexagon. I also included location as the unit of grouping in the random forests. And I'm considering 2 scales of models. First is seasonal climate, where I'm using again those 3-month aggregates of climatic variables. And for this, I chose to use anomalies in mean temperature and total precipitation, because for predicting what are those top variables, we want to remove multicollinearity between our variables. Having mean and minimum temperature were too related to each other, that having them both in the model, we would reduce the importance of any temperature variables. And similarly for the demographic variables, we only had population density because total population and older populations were highly correlated with the percent of the county that were urban. And we also looked at monthly climate. So instead of 3-month aggregates, looking at monthly aggregates to compare prediction under both of these timescales to understand what might be the best climactic timescales for this. And I'm taking a page out of weather prediction to be able to identify those top variables. So I'm essentially running an ensemble of 10 random forests. So based on wherever the data starts for fitting the trees, this is a random process, and splitting at each of the variables is random. So running 2 trees and comparing the top importance variables, they can change slightly based on the randomness inherent in these models. So I'm utilizing multiple models and looking at ranks of variables overall to identify what are those top important variables. So it's like shifting the inputs to a weather model and seeing what are the potential outputs and changes across them. And as we're moving forward, some of the next steps that I'm considering are comparing these random forest to more of the simple historical models. So a negative binomial and an autoregressive 1 model that we saw performed well in the West Nile virus challenge. And as well as comparing for prediction wise, do we get better prediction if we do a kitchen sink approach of just throwing in every possible variable? By doing the seasonal and the monthly random forests, we might be able to identify what are our top variables, but do we sacrifice any prediction accuracy by doing this? And our hope through this is to identify important climatic variables, which can lead to identifying relevant NOAA products and research directions that can be integrated into predicting mosquito-borne diseases and other climate-sensitive diseases moving forward. So I want to thank the huge number of people who have been involved in this process, and especially all of the teams that participated in the West Nile virus challenge, as well as data sources that were provided here, and everyone from NOAA, CDC, and UC Davis that have provided input and help throughout this whole process. So thank you so much, and I think we have about 10 minutes left.
Thanks, Karen. Very nice talk. The floor is open to questions. I'm seeing one coming right here. Can you explain what factors influence the choice of the other comparison models, not the ensemble?
Yeah, so we had chosen a variety of different kind of levels of complexity of models. Let's see if I can turn my camera on. Oop, I can't yet. So we'll just talk. So varying levels of complexity from very, very simple, kind of rather stupid models, which were the anything is equally probable and cases will never occur, because on the whole scale, such a small proportion of counties each year actually report West Nile virus. And then pulling in more, increasing the smartness of our models by including more of the historical data variation and counts across time, which were our negative binomial, and then the autoregressive time series analysis, which was trying to pull in ordering of counts across time. And then the ensemble was just bringing together all of the different models across time.
Okay, great, thank you. I'm not seeing any other questions, so I'm going to ask a couple here. And this is very, I'm not sure I can get the question right here, but you said something here about how the heterogeneity of the models made it hard for you to compare the different model classes. Could you just say a little bit more about that?
Yes. So no two teams utilized the same modeling approach when they were forecasting. So we had sample sizes of kind of one, and grouping them into larger groups was kind of an art and not really necessarily reflecting exactly what we were trying to capture.
Okay, got it. Can you tell us just more generally about the kinds of strategies that some of them that people used?
Yes, there were some that were using Bayesian spatiotemporal approaches, so in-law, integrated nested Laplace, hurdle models. There were some boosted classification trees, more regression-based, either more of a generalized additive or linear model. My brain is going. And then there was an empirically weighted distribution which happened to be one of the more top scoring models, where they essentially just took what were the incidences across time weighted by county or state to predict future in there as well.
Got it. So that may be relevant to this question that came in here on Q&A. The patterns in the calibration plots make me wonder about regime switching, hidden Markov models, or hurdle models. Can you say a little bit about that?
So let's flip back there so everyone can look at those plots. There, which didn't actually, oh well. So yeah, some of the variation, it wasn't necessarily held across the same. So that could be an area to further look into, maybe which models actually had those variation in impacts, and was it related at all to which modeling class was utilized. One of the things I thought was really interesting was our negative binomial model. Let's see if I can flip back really fast. Also exhibited some of the under prediction, over predictions that we were seeing from other teams as well. So interestingly, our historical data model had some under over prediction miscalibrations as well. But I'm not as familiar with more of the hidden Markov processes that were asked about. So if there are other more specific questions, feel free to hop in and ask them.
Okay, well, I'll throw out some more questions here. I'll fill up the time if nobody else has questions. But I want to go back to this your autoregressive model, and thinking about the notion of the simpler model being preferred in some sense. All other things or many other things being equal. So one way to the perhaps provocative way to put it is to say, well, maybe you've got some evidence there that says that you should just go with an autoregressive model and not worry about all the other complexity. That's putting words in your mouth, but I'd love to hear your response to that.
Yeah, at the moment, we're thinking all of our historical data models were performing really well. And in the historical data, like however many cases we had occurring already pulls in the climactic impacts and mosquito populations and land use and demographic sorts of influences might already be quote unquote baked into the historical cases that we're already seeing. So being able to as we're trying to add in more variables, we might be overfitting because that information is already present potentially, and being able to pull apart what part of the historical cases is due to climate or demographics or differences still needs to be further elucidated overall. But yeah.
Okay, another question here came in. How do you deal with uncertainty challenges relating to predicting over a long period? Given that you were going from a period of 9 years for the AR model.
Yeah, so across all of the different models that I was talking about, the AR one, and then as we get down into the random forest models, I was fitting over multiple years to try to capture actually the uncertainty and variation that we can get from year to year. Because if we fit just 1 year, we might have a good understanding of what happened in that 1 year, but that doesn't tell us, does that pattern hold or those influences hold across time? Was it just happened to fit well for this 1 year? So we want to understand the consistency kind of in our estimates as well as the differences overall. So having that uncertainty across multiple time periods and years helped us better understand and try to address capturing all the heterogeneity and uncertainty that is in the prediction over time.
Okay, fair enough. We were almost out of time. I just want to see if I could get one more question to you. What happened in 2012 and 2018? Because it looks like both of those years, the predictions collectively tanked. Yeah, right.
Yes.
There. What's with those dips? Do you have any idea?
Dips. Let's back. So if we look more at what was happening time series wise in those years, 2012 was an outbreak year overall, where we had large numbers of cases occurring, I think, predominantly in Texas location that year. And then 2018 isn't much difference, but I'm pretty sure it was some difference, like a larger difference in where actually the cases was occurring over time. So more back to historical sudden changes or differences than what we'd previously been seeing, I think was related to difficulties in those years. Okay.
Got it. Thank you. Well, it's just about 1 o'clock. So I think that's probably a good time to end it here. I want to thank you, Karen, for the interesting and nice talk, a little bit different from what we've been hearing from many of these webinars, but that I consider to be a really good thing. And so it's great to hear about a different style of modeling. So thanks everybody for attending, and hopefully we'll see you again. I think our next webinar is on November 18th, rescheduled slightly for the Thanksgiving holiday. We hope to see you then. Thank you.